So what we've done so far is we've defined the finite element structural model. We've solved for the eigenvalue and eigenvalues and eigenvectors, the natural frequencies and normal modes. And we've inspected the results to make sure that we're satisfied with our mesh. And at this point we are. So the next step is, based on the natural frequencies and the mode shapes, we need to decide how many modes we're going to include in our hydroelastic analysis. So based on our results, I've chosen 18 modes. Now this may require some iteration to determine what's an appropriate number for convergence, but I've chosen 18 modes in this problem, and so we're going to go to the next step. Now this step is relatively short. What we need to do is we just need to do some processing in advance. So we could do this and coupled with the subsequent step, but I've chosen to break it up into 2 steps. So let me open up the next input file, and that is eigenpost.txt. So that is here. So it's post-processing. We need to do a little bit of post-processing prior to launching into the next real step of the analysis. Now, I did not save the database after the eigenview project because it didn't do anything to the database. There's no need to save it. So we're still working with the eigen database, the database that we saved after calculating the normal modes and natural frequencies. So the first step here is I've defined a variable that specifies how many modes I'm going to include in the analysis. And then we read the database. Now, if we look at that file, we see that it's 9.3 megabytes, which is not big at all. If we kept those stiffness matrices and the sparse matrices in, it would be quite a bit larger than this. So, and that's going to slow things down, and there's no reason to keep that stuff in there. So then the next step is not required. It's just I kind of like to do it. So the first 6 modes coming out of the eigenvalue analysis, in this particular case for free structure, are rigid body modes. But there's actually no guarantee that they're, say, pure surge, pure sway, pure heave, and so forth. So I'm going to replace those first 6 modes, with exact rigid body modes. The other reason I'm doing that is because the modes that come out of the eigenvalue analysis are mass normalized. We know that. And I kind of like to keep those rigid body modes not mass normalized, but actually normalized to a unit displacement. In other words, a unit surge, a unit heave, a unit roll, and so forth. And that way the mass matrices and hydrostatic stiffness matrices associated with those modes will be the same matrices that we would have if we were just doing a purely rigid body analysis, hydrodynamic analysis. So I'm going to define those modes. The command rigid modes will do that for us. It's going to put the modes in this variable RB modes, and it's going to calculate the modes around the CG. Now I'm going to then put these modes, so what comes out of here is basically is a matrix. RB modes is a matrix that's is in number of degrees of freedom, the number of rows, and the number of columns is going to be 6. So I'm going to put that matrix into the first 6 columns of the matrix that contains the eigenvectors, .phi. So the next step then is also not required, but I'm going to, there are other ways to do it, but this is how I'm doing it. I'm going to just copy the number of modes, in this case 18, from .phi to a array called phi. And then I'm going to write that for future use. Write that to a file for future use. And then I'm going to save the database, and I'm going to save it back into Eigen. So it's I'm going to there's a little bit of modification, right? So the mode shapes have been modified, and I've created this thing called this matrix called phi, and that's going to be an Eigen. So let's start this up and see what we get. By the way, now that we've run two projects, we have two options in here in recent. We have the Eigen and we have Eigen View. Neither of those are what I want to do. I want to do Eigen Post. So I'm going to, but it's still in this folder. So we have Eigen Post. All right, so I am just going to file this in. This is going to be very quick. It's done, and we've saved the database. Now, if we look at this, this command here, it has written eigenpost.phi, this file here. So it's written those mode shapes to this file with the .phi extension. Now, let's look at what we've got in this database. We've been talking about it quite a bit, and we've been using it, so I probably should have covered it a little bit more beforehand, but in the tutorial videos for Hydrogen, I covered as well. So we can use the ls or dir command to get a listing of the members in the database. So if I use ls, so these are the members in this database. These are the matrices, right? So you can see we've got our variables that we've defined, and the numbers in parentheses are the dimensions of the array. In this case, it's just a scalar, so it's just 1. And we can see that, for example, where's phi? Here, phi is what we defined, right? Our first 18 modes, and 34,572 is the number of degrees of freedom. So phi is this matrix here, and the mass summary that we created by that mass summary command, and this is the 6x6 mass matrix, right, is here. I want to point out that if an array starts with a dot, with a period, that means it's been generated internally in the program. So my recommendation is don't name anything with a period, because you might overwrite something that the program has generated automatically. Anything that the program needs, it does not use. It always puts a period in front of it. All right, so we see that we have 15.2 megabytes now. Now let's look at the next steps. We're not going to do them in this video, but I want to discuss them. So the next step is optional. It depends. So if you'll recall, we need the hydrostatic stiffness. So if we go to that PowerPoint slide from an earlier video, where you may, if you watch those videos, you may recognize this slide that gives the formulation for the hydrostatic stiffness. Now this is the full formulation, and if we're going to use this full formulation, then we need to calculate sigma Lm, which is the internal stress in the structure as it's just sitting there in calm water. We don't have that yet, right? We have to calculate that. So that would require us to do a static analysis. And so if we're going to use this full formulation, that's the next step. And I'm going to go over that. That will be the next video. However, as I've mentioned, some people only include the term that involves N3J. So if you look at that first integral there, it's actually the first term in that integral. If you're going to do that and not include the full term here, then you don't need to do the next step, because that term will be calculated later in a subsequent file. And you can, if you're satisfied with that formulation for the stiffness, then you can skip this static analysis step. But for the next video, we're going to do the static analysis of the structure to determine sigma Lm.